Let us have a look at this quast results. But before we look at the results, here is the script I made for running quast, and we were given this command line in the module document, and then we should make the rest of the script ourselves. Well, the header part is straightforward, right? Because the first 4 lines are always the same. You have to decide on the number of threads. I use 10 as usual. I use 10 gigabytes also as usual. And I set the wall time at 1 hour. I think quast is pretty quick, so I guess 1 hour is more than enough. Give some name to the job, and quast is a good name for this job, I think. And also the log file, where we got some text output in case something goes wrong. Yeah. When it comes to the command line itself, we can see that it refers to some shell variables, right? This is how you sort of refer to the content of a shell variable with a $sign first, and they are colored blue as well. And of course, for this to work, these variables must have been created and filled with some content. This is something you should sort of immediately realize when you see this code. Okay, in order to make this code work, I need to create the variable threads and fill it with some content before I come here, right? And the variable ref and the variable out, all this must be filled with something, created and filled with something. And that's what I do up here then. Before we come to the command line, I create a variable named threads. And it must be that name because we see it used down here. Another variable called ref here because we see it used down here, right? And fill it with this. This we were told to use, this reference genome. This is a FASTA file with some genome sequences that we use as a reference in this case. So quast can compare our contigs to this reference. And here are our contigs. The speeds, output, results. And then I should put everything into a folder. Usually we write the output to scratch. And in this particular case, we don't do it. It's unusual, you could say. The reason I would like to have the output here in the same folder that I'm running now, working, is that I want to be able to inspect that folder and click on some HTML file there, and then I find it convenient to have it here. It's not required. You can of course click your way through to the scratch disk as well if you want to do that, but for simplicity I put it in a folder here. And you can see over here now, here is my module 7 folder where all this is stored, and here is the actual script, right? That's the one you see over here, quast.sh, the shell script. And here is the container, and of course that's also important that the name you use here of the container file is exactly the same as your container file. So if you have downloaded a different version of quast and the name here is different, you must edit here accordingly. Yeah, and then you can see I've been running quast here. I got a log file with the quast and then the job ID. Always include the job ID in the log file name, I would say. That's really convenient because you otherwise forget it. Yeah, here are the contigs we used as input, the FASTA file. And it must be in this folder as well, since there is no path here. This one is in a different folder, the reference, so we don't see the reference here. That's in a completely different folder somewhere, and that's fine. Let it be where it is. Yeah, and then we should inspect the results, and the results are now here, right? The quast output folder. This is being created by quast. So let me click into it, and here you can see a lot of results. But we will only focus on this HTML file this time. There are some other folders, for instance, this basic stats here usually contains some useful results that you can read into R and so on. But not this time. I will only focus on this report.html file. So, since we are now running RStudio inside a web browser, we can simply just click on this and select View in Browser, and it will open here as a separate tab, right? Inside the same browser, next to RStudio, you could say. So, this output report contains a lot, and I will just focus on some few things now that I think is important. The first is this figure. It may appear over here, depends on the size of your window, but here it is now. And this has also multiple tabs you can click through and inspect. I will only look at this called cumulative length now, which I believe is the most important and most informative of these tabs. So what do we see here? First of all, we see two curves. One is our contigs and the other one is the reference. The red is our contigs, the broken black line is the reference. What does this show? Well, on the x-axis here we have number of contigs. So there is apparently 31 contigs in our spades contigs. And on the y-axis we have the number of megabase pairs we get if we add together the contig lengths. And this is seen here. If I go here after having added one contig, and contigs are always sorted in descending order here by length. So the longest contig is the first one. And we can see that after having included one contig, we are up to 685,000 bases. If we go to the second contig and include that as well, add to the first one, right? That's cumulative length. Then we are up to 919,000, and we can go and include also the third contig, and we are over 1 million now, right? And so on. So for each step we take to the right on the x-axis, the increase in the length increases, right? And less because the contigs we add now are shorter and shorter. And at the end here it's almost flat because the contigs are so short at the end here. So that's the red curve. The black and broken curve is almost the same here. And that's really unusual, I would say. And why is it very similar? Well, it is because the reference in our case is not the complete genome. It's simply another set of contigs for the same genome. And that's why it grows in a very similar way too, because obviously the assembly of this reference turned out quite similar to the assembly this time with our contigs, because they were both Illumina data, so they're not identical because it's two different sequencing runs, but they are quite similar, I would say. If you used a complete genome as a reference, and that is perhaps more commonly to do, then you will see that, let's say it has one single chromosome, this genome. Then you will see the first contig, which is not really a contig but a chromosome, will go directly from 0 and up here somewhere, and then it will be flat after that. So the dotted line would go in one contig up to the full genome length and nothing more. Or if it has a couple of smaller plasmids, this genome, then you will have first a big chromosome, and then it will grow a little bit and then flat due to the plasmids, and then it will stop. Yeah, but now we have the same number of contigs. I think it's exactly the same number of contigs, and the contigs are also almost of the same size, you can see, in the two cases. So that's unusual then. Okay, but this figure here is usually nice to look at because it tells you how big is your sort of genome now, the red, compared to the reference. And they should end at approximately the same height here, right? If the reference is either higher up, it means you haven't managed to capture all of it, or it is further down. It can also happen that the reference is shorter than then you have either added some extra or the reference is lacking something compared to your genome, right? So both all these variations can be seen depending on the reference and the genome you have sequenced. Because finding a good reference to compare against is not always so easy for prokaryotic genomes. Even genomes from the same species can differ from each other quite a lot. Yeah. Let's go up here and have a look at these numbers that are results listed over here. Notice that if you hold your mouse over one of them, a small black window pops up with some explanation. Well, that's nice. You can get a good explanation for what each term here is. Yeah. So this number here measures how well your contigs cover the reference. So you have to have a reference in order to get this result here in the output. If you can use quast without references, and then you will not see this. Then you will have only a few results listed here. In this case, we have over 98% coverage, which is very good, right? It means that if you take the red contigs and align them to the black, the reference, you will cover almost the whole reference. So it means that your contigs capture the same, more or less the same genome with a few percentage difference. But this is very good. 98% I would say is very good. Everything about 95 I think is very good. So it means that you can think of it as a big picture. You have managed to reconstruct almost the whole genome here. So that's a genome fraction, and that's perhaps the most sort of the first thing I would look at. But notice the figure here also tells us this, right? We can see it here, that the red and the black, they stop almost at the same height on the y-axis, right? So this is just a number to confirm that. The other thing I would look into is this misassemblies thing. So a misassembly is an indicator that when you compare your contigs to the reference, there are parts of the reference which is also found in your contigs, but they are not found in the positions they should according to the reference. And let me just click on this extended report, because then we get some more information here on misassemblies. And you can see there are three ways of doing misassembly: relocations, translocations, or inversions. And this is a case of a translocation, the single misassembly here. And only one misassembly is also very good, I would say. A single misassembly is good, and as long as it's like 1, 2, 3. If it's like 10 or 100, then it's another story. I would like to say, let's look at this translocation then. This is the only misassembly found by quast, and it says translocation is the number of translocation events among all misassembly events. Translocation is a misassembly where the flanking sequence sequences align on different chromosomes. And notice the word chromosome here. Quast sort of assume that the reference you have is a complete genome. And of course, if one part of a contig aligns to one chromosome and another part of the contig aligns to a different chromosome, or the flanking sequences, right? Then it's a bad sign, because they should be on the same chromosome, right? Otherwise they shouldn't be in the same contig. But now you must remember that in our case, the reference is not a complete genome with chromosomes. It's also contigs. And these contigs may of course be sort of cut at different positions compared to our newly made contigs here now. So I would actually say that as long as the reference is not a complete genome, I would consider a translocation misassembly as not really a misassembly at all. Because it can just as well be because the contigs have been split at different positions now compared to the last time we made contigs. Yeah, but misassemblies is something we always look at. How many do we have? Because that is sort of, together with this coverage up here, something about how well the assembly look like. The third result I would look at is this one here. Mismatches per 100 kilobase pair. And how should we understand this? Well, when quast aligns our contigs to the reference, it will not require 100% identical match. There is some substantial amount of mismatches which is allowed, and still quast will say that the contig matched. So even if you have almost 100% of the reference being covered, it can still be quite a lot of mismatches in there. And this is then the number that reveals this. This is the number of mismatches per 100,000 base pairs. So always have a look at this one. For instance, we will later in this module also assemble this genome based on nanopore reads, long read technology, right? And then we get better assembly in terms of longer and fewer contigs. I'm sure you will see that. But the mismatches per 100,000 base pairs will be larger, because the nanopore long reads, they are very long, and that's good, but they also have a lot of errors in them. So they align to the reference, but poorer, you could say. The alignments are poorer, more mismatches in them. Yeah. How about the N50 that we talked about in the module document? Well, it's listed here as well. And here you can see it's 194,376. And that's actually then the length of a certain contig. And what is that contig? Well, we can actually understand this value at least a little bit from this figure here, because we know that if we sum all contigs, it's 2.1 million, right? Can you see that number there before the red spades contigs? 2,142,237. Yeah, that's the sum of all contigs. When do we reach half that length? When we climb up here, around here somewhere, right? Here, I think. Here we are. Yeah, is it here? When we go from contig 2 to 3? Yeah, I think so. It's when we go from contig 2 to 3. Here we are below halfway now, less than a million. And here we are above halfway, 1.1 million. We know that the total is 2.1. So it's actually contig number 3 where we cross halfway through to the top. And then this length here is actually the length of that contig number 3. If you notice at the top there are some other similar statistics. For instance, this one, NG50. What is that? Well, it's very similar to N50, but instead of asking where do we sort of climb to the top of the red curve, we say where do we pass halfway through the top on the black curve? And the length of that contig. And that will of course be exactly in the same place here now because they reach the same height, right? More or less. So it's still the third contig where we cross through. So you will see that this value is actually the same again. It's the length of that third contig. Yeah, you can read about the other, there are all kinds of variations of this N50 statistic here. You can always look into them if you like. But I think that as long as you have a reference, we don't care that much about the N50 value. We care about this genome fraction, the number of misassemblies, and the base pair quality. But none of these three are available if you don't have a reference. And then we have to look at the N50 as the only thing we can sort of hold on to. Okay,